Right. So one of you tell me, what is a wave? What is a wave?
And it's like it carries energy.
Energy and what else? Waves carry energy and what? There's one more thing that they carry from one point to another. Okay. Waves carry energy and momentum. Fine. So obviously electromagnetic waves also, they carry energy and momentum from one point to another. What kind of energy do you think electromagnetic waves will carry? Yeah, Shashank, good evening. We just started discussing about electromagnetic waves. So what kind of energy do you think electromagnetic waves will carry?
They're electric and magnetic energy.
Correct. Electric and magnetic energy. The name itself suggests, no? Electric and magnetic energy. And they carry it by means of electric and magnetic fields. They produce electric and magnetic fields, and energy is stored in those fields. Okay. We'll discuss in detail how this works. But before that, one of you tell me, what is Faraday's law? Or at least the formula for Faraday's law?
Minus d phi by dt equals d induced.
Correct. Induced EMF is minus d phi by dt. Now, basically what Faraday discovered is that a time varying magnetic flux produces an electric field. Okay, and we discussed different ways in which the EMF can be induced. There are two methods. One is motional EMF, the other is induced electric field. Okay, how is induced electric field produced? A time varying magnetic field produces an electric field. That is what we call as induced electric field. So all that was discovered by Faraday. So a magnetic field which varies with time produces an electric field. Okay, so that is established. Magnetic field can give rise to electric field. Okay. Then there's another scientist called Maxwell. He performed some experiments on these things itself, magnetic fields and all. Now you consider a straight wire. Okay, assume it is very long and carries a current I in it to the right. A wire carrying a current I at a distance x from itself, how much magnetic field does it produce? An infinite straight wire carrying a current I, how much magnetic field does it produce at a distance x from itself?
Mu naught I by 2x.
Mu naught I by 2 pi x. Okay, the magnetic field at a distance x will be mu naught I by 2 pi x. Okay, due to an infinite straight wire. And what is the shape of the field lines? They are circular. Okay, with the center of the circle lying on this straight line, straight wire. So current is to the right, point is upward. Ideal cross R if you take, field will be towards you. So this current wire produces a magnetic field somewhat like this. Okay, at a fixed distance x from itself, the field strength is mu naught I by 2 pi x. Now, what do you think will happen if some elements of this wire are missing? will the same field get produced, or will a slightly lesser field get produced, or an even stronger field get produced? Rishi, what do you say? If we remove some elements from this wire, okay, will the field strength at that distance x still be the same? Will it be weaker or stronger?
Sir, I think it will be weaker.
Definitely it will be weaker. Every current element is involved in the production of magnetic field at this point. Okay. The resultant magnetic field of all current elements is mu naught I by 2 pi x. So if some current elements are missing, the field should definitely be weaker. Okay. But Maxwell observed one thing. He again took a straight long wire, but this time connected a capacitor in between. Consider a parallel plate capacitor itself. So basically what we are doing is we are creating a gap in the wire. Capacitor plates won't be touching each other, no? So there is a gap in the wire. Fine. Assume the capacitor is being charged. Okay. When a capacitor is being charged, there will be a current in the branch consisting the capacitor. Once it is fully charged, current will become zero. When a capacitor is fully charged, it behaves like an open switch. But while it is being charged, there will be some current in that branch. Okay. Let's say the current in that branch is the same I, which we took in the straight wire. This current and this current, assume they are equal. Now you consider a point at a distance x from the wire in the second case, the lower case where the capacitor is connected. Okay, let this distance be x. Consider the point here. Now tell me, should the field, like from what we know about magnetic field produced by current and all, should the field be the same as the field created in the upper case? Should it be stronger or weaker if a capacitor is introduced? Currents are equal, but there's a capacitor now. We have created a gap in the wire. So the magnetic field produced at this distance, should it be mu naught I by 2 pi x, weaker or stronger? Isha, what do you think? Okay, Shashank, what do you think?
The current flowing will cause the capacitor to get charged, right?
Yeah, if the current is flowing, the capacitor is either getting charged or getting discharged. Yes, one of those things will be happening.
I don't know whether that will reduce or increase the magnetic.
But based on current, you tell. Simply based on current. Don't think about charging and discharging of capacitor or what a capacitor does. But based on what the current does, you tell. Should it produce the same field, stronger field or weaker field?
Same field.
Aren't some elements of current missing when you introduce a capacitor?
Oh, yeah. Because
Definitely, there is a gap between the plates, right? Okay, I'm telling this to all of you. So it's like some elements of the wire are missing. There's a gap, there's vacuum. So definitely a weaker magnetic field should get produced. But Maxwell observed that when the capacitor is getting charged or getting discharged, the magnetic field produced in this case is same as the magnetic field produced above, mu naught I by 2 pi x itself. Now there is a current element missing, or there are some current elements missing in this space, the space that I am marking in red. Whatever wire must have been present there is not present. Okay. So some change in magnetic field should definitely be there, but Maxwell observed that there's no change in the magnetic field at all. Okay, the same magnetic field gets produced whether there's a capacitor or it's completely a wire. How do we explain this? What is compensating for the, or what is covering or making up for the magnetic field lost due to the missing elements of current? What could be covering up for it? The only way to explain this is the electric field present between the plates of the capacitor. Now suppose current is flowing like this. Let's say this is the positive plate, the opposite side is the negative plate. Then you know there will be an electric field from positive plate to negative plate. Okay. And when the capacitor is getting charged or discharged, this electric field will be varying. Okay. The formula or the expression for electric field between the plates of a capacitor, each plate will produce sigma by 2 epsilon naught. Both plates will produce the field. So net electric field between the plates of a capacitor, parallel plate capacitor, is sigma by epsilon naught. You can write that as Q by A epsilon naught. Now, as the capacitor gets charged or discharged, that is, when current flows in the wire consisting the capacitor, Q is a variable. And if Q is a variable, automatically the electric field between the plates becomes variable. And Maxwell concluded that it's this variable electric field which is producing the missing magnetic field. Okay, like due to those small current elements which are missing, some loss should have happened, should have occurred in the magnetic field, but it's not happening. So Maxwell concluded that it's this variable electric field between the capacitor plates which is making up for the lost magnetic field. So from these experiments, Maxwell concluded that a time varying electric field produces a magnetic field. Okay, Faraday found that a time varying magnetic field can produce an electric field. Maxwell found that a time varying electric field can produce magnetic field. So one produces the other. But it has to be time varying, only then it can happen. Constant magnetic field cannot produce electric field. Constant electric field also cannot produce magnetic field. Okay, they did experiments and found it out. Okay, so let's discuss this a little further. So basically what is happening, the electric field that is present between the plates of the capacitor, it keeps changing when current passes through those wires. So effectively what is happening is this time varying electric field that is present in the space between the plates of the capacitor is producing a current like effect. Means it is producing a magnetic field which the current would have produced. Fine. So it's producing an effect that a current produces. It behaves like a current. Okay. So a time varying electric field behaves like a current. It's producing a magnetic field which a current would have produced. So that's why we say it behaves like a current. So we can say that time varying electric field is equivalent to current, and he named that current as displacement current. Fine. Usually current is nothing but flow of charges. Electric current is rate of flow of electric charge. When charge flows through a cross section, we say there is current through it. But here that is not what is happening. There is a time varying electric field passing through a cross section. Okay. So if electric field is varying with time, automatically the flux will be varying with time. Fine. So we should properly say a time varying electric flux behaves like a current, and the current which it is equivalent to is what we call as displacement current, ID. So this is different from the conventional current. The usual current is the rate of flow of charge, but here current is not due to flow of charges. It is due to a time varying electric flux through a cross section. Okay. We can even derive an expression for it. Assume the area of the plates is A. Okay, plates of the parallel plate capacitor, let the area be A. Electric field between the plates will be Q by A epsilon naught. That's the net field between the plates. Then you can say that the electric flux through a cross section parallel to the plate will be field multiplied with area. You don't have to bother much about the angle between them and all. Field will be from one plate to the other plate. And if you take a cross sectional area like this, the area vector also will be in this direction itself. So field direction, area vector direction are the same. So flux becomes EA. It's EA cos 0, EA. Now E is Q by A epsilon naught and area is A. So the electric flux becomes Q by epsilon naught. Therefore, you can say that the charge on the plate of the capacitor is total electric flux multiplied with epsilon naught. Fine. Now we want to know how much current that time varying electric flux is equivalent to. We want an expression for displacement current. Okay. For that, the logic that Maxwell used is, see, this straight wire and the wire consisting the capacitor were producing the same magnetic field. So the logic he used is, this time varying electric flux, whatever is there, it should behave as this same current I, because it's producing the same magnetic field which the current would have produced, no? So all the time varying electric flux that you consider, I mean, that is present between the plates of a capacitor, if you consider, it produces the same effect as the current in the wire is producing. So we can say that I is equal to dq by dt, which effectively becomes the time derivative of epsilon naught into electric flux. So epsilon naught d phi by dt. This is the formula for displacement current. In any region of space, if electric flux is varying, then you can say that this much current is passing through that cross section. Okay, like in that region of space, if you consider a cross section, then the expression for displacement current would be epsilon naught d phi e. Phi e stands for electric flux divided by dt. Fine, let me repeat this once. Maxwell found that when a capacitor is placed in a long wire also, it produces the same magnetic field as the straight wire would have produced. Now, when there is a capacitor introduced, there are some current elements missing. Even though there are some current elements missing, the same magnetic field is being produced. So he concluded that the time varying electric flux between the plates of the capacitor should be behaving like a current, must have been behaving like a current and producing the magnetic field which the original current produced. Okay, so if you consider all the time varying electric flux between the plates of the capacitor, it is equivalent to the net current I flowing in that wire. So that way, I mean, using that logic, we derive this expression for displacement current. Fine. Now consider a situation like this. Let's say this is a capacitor plate having a circular cross section. Parallelly, there is another capacitor plate. So it's clear we are looking at them from an angle. So one edge of the plate will be out of the screen, the other edge will be behind the screen, both plates. Fine. Assume a wire is connected. If a current I passes through this wire, then the charge on the plates of the capacitor will be a variable. And if charge is varying, the electric field will also be varying. You can visualize the field lines from the positive plate to the negative plate. We are considering parallel plate capacitor because it's the easiest case. It produces a uniform electric field between the plates. Fine. So if you consider this complete flux, the equivalent current is I itself, whatever is the current flowing in the wire. But if you consider only a part of this flux, okay, let's consider maybe only this much. So if you consider only a part of the flux, then it's obvious you're not considering the effect of the entire flux. Then the equivalent current will not be equal to the original current in the wire. For example, suppose the total area is A and you take only an area of A by 3, 1/3 of the area. Okay, you take a cross section whose area is 1/3 of the plate's cross section, plate's area. In 1/3 of the area, because the field is uniform, you'll have only 1/3 of the flux passing. Okay, then in that 1/3 area, if you visualize the field line separately, it's like this. Okay, through that 1/3 area of cross section, there are only some field lines passing. The flux is total flux divided by 3. Then see, this flux is also variable because the capacitor is getting charged, electric field is variable, flux through the entire area is variable, flux through a small part of area is also variable only. So this is also equivalent to some current. The current which this will be equivalent to is epsilon naught derivative of 5 by 3 with respect to time. So basically this becomes 1/3 of the total current in the wire. So if you take only 1/3 of the area, you'll get 1/3 of the current because the flux is 1/3. So basically the idea is if you want to find out displacement current, you need to know how much flux you are considering because it is the time varying flux which produces displacement current. So if you consider all the flux between the plates of a capacitor, the current that it is equivalent to is the current flowing in the capacitor wire itself. This current will be same. But if you consider only a part of the flux, let's say 1/3 of the flux, then the current equivalent to that 1/3 of the flux will be 1/3 of the total current. That way. So questions based on this are quite common. They can give you a ring of radius r by 2 or r by 4 and ask you what is the displacement current passing through it. You just need to see how much or what ratio of flux is passing through it. That much ratio current you can take. So is the idea of displacement current clear? Any doubt in this? Let's try some problems based on this. First. Okay. To get displacement current, we need a time varying flux. No? So the capacitor should either be getting charged or getting discharged. Now, if you connect the capacitor to an AC source, that charging, discharging will keep happening all the time. Fine. Let's say the EMF equation is given E naught sine omega t. You can easily write what is the time period of this function and all. I want you to find out how much is the displacement current between the plates of the capacitor at t equal to 1/6 of the time period. Okay, try this all of you. When I say displacement current between the plates of the capacitor, it is understood that all the flux is included. Okay, so how much is the current equivalent to that? Try. Any answer, anyone? At least any idea how to solve? Listen, there is a time varying electric field between the plates of the capacitor, which produces a time varying electric flux. And when there is a time varying electric flux through any cross section, it's like a current is passing through that cross section. That current is what we need to find out. Now you are asked to find out the total displacement current between the plates. Total displacement current between the plates will be equal to the conduction current in the wire. So the question is indirectly asking you to find out how much current is passing through the capacitor. That's all. Okay. One of you tell me, when an alternating EMF is applied across a capacitor, how to write the current equation? Isha? No response. Rishi?
Sir, E naught by Z sin
How much
omega.
will Z be if there is only a capacitor?
Sir, you just don't have to put R's value and XL's value. I need to
R
find
is 0, XL is 0. So Z becomes equal to? Tell me the formula for Z.
XC minus XL whole square plus R square whole root.
XL is 0 here. R is also 0 here. So how much does Z become?
E square. XC basically.
That's all. So you'll write I is equal to E naught by, in place of Z, you have XC. And what else? Sine?
Sin omega t plus pi by 2.
Plus pi by 2. In a capacitor, we know current leads the EMF by a phase difference pi by 2. Okay. See, if you don't remember that also, you can use the tan phi naught formula. Tan phi naught is XC minus XL divided by R. Now XC is there in this question, but XL is 0, R is 0. So a positive number divided by 0 tends to positive infinity. And tan of what angle is positive infinity? Plus pi by 2. That way also you can tell that the phase constant is plus pi by 2. And sine theta plus pi by 2 is cos theta. Therefore, the current equation effectively becomes E naught by, Rishi, you only tell me, what is the formula for XC?
1 by L omega, sir.
L is for inductor.
Oh yeah, it's C omega.
1 by C omega. So goes to the numerator. Effectively, the current becomes C E naught omega sin omega t plus pi by 2. I'm writing it as cos omega t. That's all. That's the current passing through the capacitor. And that is what the current question is asking you to find out, but at a particular instant. We got current at any time. As a function of time we got. We need to tell its value now at that particular instant, T naught by 6. Okay. How much is the time period of E naught sin omega t function?
Two pi by V.
Time period T naught is 2 pi by omega. Then the given time is T naught divided by 6. That is 2 pi by 6 omega. That's nothing but pi by 3 omega. So we'll substitute this in place of T now. That's all. Therefore, the current at that time becomes C E naught omega cos omega into pi by 3 omega. Omega gets cancelled. You will be left with cos pi by 3. Cos pi by 3, cos 60 is 1 by 2. Therefore, the answer is C E naught omega by 2. That's the current flowing in the wire at that moment. And the same will be the displacement current between the plates of the capacitor. Because you are asked what is the total displacement current between the plates. If they only ask you what is the displacement current in half the plate area, for full plate area it is this much current, then for half plate area it will be half of this current, because in half area half flux only will pass. Okay, is the solution clear to all of you? Any doubts in this? Anugrah, did you understand?
Yes, sir.
Okay. Isha, what about you?
Yes, sir.
Fine. Let's try another question. Suppose there's a parallel plate capacitor. Plate area is given, let's say 4 centimeters square. Okay. And distance between the plates is given 0.5 millimeters. Okay. Electric field between the plates of the capacitor is varying at a rate, like we know when the capacitor is getting charged or discharged, the charge will be changing, varying. So the electric field will also be varying. So let's say electric field is varying at a rate some 2 volt per meter per second. Okay, volt per meter is the SI unit of electric field. Newton per coulomb you can write, volt per meter also you can write. It's the same. So let's say it is at a particular moment, it is changing at this rate, 2 volt per meter per second. So this is not E actually, it is dE by dt. Rate of change of electric field is given to you. Okay, I don't think you need the distance between the plates anyway. Find out the displacement current between the plates. And just to remind you, displacement current equation is epsilon naught d phi E by dt. You can keep epsilon naught as it is, don't substitute its value. Solve this quickly. Okay, I got one answer as 8 into 10 power minus 4 epsilon naught multiplied with A again. And another answer as 8 into 10 power minus 4 epsilon naught only. Let's see. Rishi, how are you trying to solve this?
Sir, I'll find the I equation first.
How will you get the I equation? That is what the question is. Okay. Seshank, explain what you have done. Okay, you are saying A is ampere, that's fine. So 8 into 10 power minus 4 epsilon naught. How did you solve?
Since it's equal to d phi E by dt, and flux is area into electric field.
That's all, direct. Okay. So it is epsilon naught into derivative of electric flux. Electric flux is field multiplied with area. Simple. So epsilon naught, area is area is constant. Bring it outside the derivative. Multiply it with dE by dt, and dE by dt is given to you in the problem. This is 2. That's in SI units. Area is 4 centimeters square. Convert it to meter square. It becomes 4 into 10 power minus 4. So this is 4 into 10 power minus 4. That's all. That's the answer. Therefore, the total displacement current between the plates of the capacitor becomes 8 into 10 power minus 4 epsilon naught amperes. You have to substitute epsilon naught also in SI units, then you will get the answer in amperes. Pradyun, is this clear? Isha? Fine. Try this question now. Suppose there's an electric field which varies with x coordinate and also with time, like this. E is equal to some 10 x square t cube. Let's take it like this. So from point to point, it will change as you move along the x-axis or parallel to the x-axis. Based on x-coordinate, the field will change. And at a given x-coordinate, time to time also it will change. Okay, that's the kind of electric field given to you. And this is in the I cap direction. SI units, so volts per meter. Assume there is a square loop. Consider a square of side, say 2 meters, placed parallel to YZ plane at, let's say, x is equal to 4 meters. Okay, when there's a surface parallel to the YZ plane, it should have a particular x coordinate. Okay, so let's say it's placed at x is equal to 4 meter. I want you all to calculate the displacement current through this square at, let's say, t is equal to, take 2 seconds. Okay, visualize the field and solve this carefully. And keep epsilon naught as it is. Other values you substitute. Any answer, anyone? Okay, let me help you visualize the situation. Consider the XYZ planes like this. So your screen is the XY plane, Z is perpendicular to your screen. Now it is given to you that there is a square of side 2 meters placed parallel to YZ plane at x is equal to 4. Okay, let's consider that square first. Okay, since YZ plane is shown in green, I'll take the square in green itself. It's kind of like this. And the square is placed at x is equal to 4. I think I should shade it a little. This is the square that we are talking about. Half the square is out of your screen. The other half of the square is behind your screen. It's like this. And it cuts the x-axis at x is equal to 4. That is what is happening. Are you all able to visualize this? It's a square parallel to the YZ plane. Okay. Now, how is the electric field? Electric field is 10x square t cube I cap. Means electric field, like for positive x coordinates and positive times, electric field is in the positive I direction. Okay, Anugraha is asking, sir, can we consider x to be constant while differentiating since the question has specified x is equal to 4? Yes. See, displacement current through that square depends on how the electric field through that square is varying. It doesn't matter what is the electric field at other points. Fine. So through this square, the electric field passing, the general expression is given 10x square t cube. But all points of the square have the same x coordinate, x is equal to 4. Therefore, electric field on that square is 10 into 4 square t cube. 16, that is 160 t cube is the electric field at points of that square. And if you know the electric field as a function of time, you can tell the rate of change of electric field. So 160 into 3, 480 t square is the rate of change of electric field. And the electric field is in the positive x direction. So it's like this. You can imagine field lines coming out of that square. or passing through that square. Okay, it is this electric field which produces a flux through that square. And because electric field is varying, flux will be varying, displacement current will get produced. Now it's simple. The formula for displacement current is epsilon naught d phi e by dt. That is the derivative of electric field multiplied with area. It's actually, flux is actually E dot A. Here you don't even have to bother about the dot product. The electric field is in the x direction. The area vector of the square loop or the square that we have considered will also be in the x direction itself. So the angle between electric field and area vector is 0. So the flux is simply EA. Area is constant, put it outside the derivative. E naught into, what is the side of the square? 2 meter. Okay, wait. Side of the square is 2 meters. So area of the square will be 4 meter square. And dE by dt is 480 t square. Now at what time were you asked? 2 seconds. Substitute t as 2 in this. 2 square becomes 4. That will be the current. Okay, it's a large value, but let it be. I mean, with if you keep E naught as it is, the number will be large. E naught actually is a very small number. Okay, 10 power minus 12. Is the solution clear to all of you? Any doubts in this? You were given a particular region, that is a square, and asked what is the displacement current through it. To get displacement current through the square, you need to know how electric flux through the square is varying. We know the area of the square. So the next thing we need is the electric field passing through the square. Now the square, every point of the square has the same x coordinate 4. Then at every point of the square, the electric field will be this much according to the given equation. Once you know the electric field, differentiate it. You'll get the rate of change of electric field multiplied with area. You get the rate of change of flux. Multiply with epsilon naught. You get the displacement current. Okay. So Faraday discovered that time varying magnetic field produces electric field. Maxwell discovered that a time varying electric field or a time varying electric flux can produce magnetic field. So one field can produce the other. That's why, I mean, in further studies, you will learn that they are both components of a single field called an electromagnetic field. But for now, we'll look at them separately only, electric and magnetic fields. Okay. Can one of you tell me what Ampere's law was? In the chapter Moving Charges and Magnetism, we had discussed. What is Ampere's law?
Mu naught I, sir. B.
What is on the left hand side?
BDL. B dot DL.
Okay, closed integral B dot dl. Okay, that's the line integral of magnetic field over a closed loop or a closed path is mu naught into I enclosed by that path. Fine. So if you consider a loop, no, any closed loop, say like this, the loop encloses an area. And if there's a current passing through this area, okay, maybe into the screen or out of the screen, we call that as enclosed current. Okay, current enclosed by this loop means, see, that loop encloses an area. Loop forms the boundary of an area actually. The current should be cutting through that area. That is what we call as enclosed current. So integral B dot dl over this loop depends on the enclosed current. And that is what Ampere said. Now you consider what Maxwell discovered. If there's a capacitor like this, parallel plate capacitor, and there's a current passing in this wire, Maxwell found that there will be a magnetic field produced in this region, as if there was a current passing between the plates of the capacitor. But is there actually a current passing between the plates of the capacitor? No. There's a time varying electric field. Charge is not flowing from one plate of the capacitor to the other. If at all charge is flowing, it flows like this. Through the battery, it goes to the other plate. It doesn't jump from one plate to the other. Okay. That's not how charging of a capacitor takes place. When a capacitor is getting charged, battery has to pull charge from one plate and the charge travels through the battery and gets deposited on the other plate. So charge doesn't jump from one plate of the capacitor to the other. So if you consider a loop like this and the area that it encloses, is there any current cutting through that area? Are there any charges passing through that area? No. So the conventional current that we consider, which is basically flow of charges, no such current is there through this loop. Current enclosed is 0 here. Okay, but there is a magnetic field. Closed integral B dot dl is not 0 for this loop, but current enclosed is 0. That means Ampere's law is violated. Closed integral B dot dl is not becoming equal to mu naught into I enclosed. Okay, so what Maxwell did is he suggested a modification to Ampere's law. Okay, because Maxwell was the one who discovered that it's not only moving charges which produce magnetic field, a time varying electric flux also can produce a magnetic field. Okay, so Maxwell suggested a small change in Ampere's law. Now it is, the changed form is called Ampere-Maxwell law, and it is written like this. Closed integral B dot dl, that is the line integral of magnetic field over a closed loop, is mu naught into conventional current plus the displacement current. Okay, Maxwell said that it's not only moving charges that produce magnetic field, time varying electric flux also can produce magnetic field. So we'll change the equation a little bit. We'll consider the effect of charges if there are any, and we should also consider the effect of displacement current. That is a time varying electric flux. So this is what is Ampere-Maxwell's law, the modified form of Ampere's law. Okay, we can write it this way also. Mu naught into the conventional current, that's the current due to the flow of charges, plus displacement current formula we know, epsilon naught d phi E by dt, through that loop or through the area enclosed by that loop, you can say. Okay, this is Ampere-Maxwell's law. Okay. Can one of you quickly tell me the formula or the mathematical form of Gauss law in electrostatics? Gauss law in electrostatics.
Sir, is it Q by E naught?
What is on the left hand side? Right hand side, Q by epsilon naught is correct.
Surface integral of B dot dl.
Okay. Closed integral of electric field over an area. Okay, we call it as surface integral of electric field over a closed surface. Okay, is equal to charge enclosed by that closed surface divided by epsilon naught. Fine, that is Gauss law in electrostatics. Basically, the left hand side is the net electric flux through a closed surface. Okay, E dot dA is electric flux. You're integrating that over a closed surface. So total electric flux through a closed surface is charge enclosed by epsilon naught. Next, can one of you tell me Gauss law in magnetism? What is closed integral B dot dA equal to?
0.
0, correct. Net magnetic flux through a closed surface is always 0. Reason being, why is net magnetic flux through a closed surface always 0?
Magnetic monopoles do not exist.
Magnetic monopoles do not exist, or you can also say magnetic field lines always form closed loops. So number of field lines entering the closed surface will be equal to number of field lines leaving. Net magnetic flux is 0. Next, Faraday's law. Okay, we discussed in today's class itself, need not repeat. Faraday's law is basically induced EMF is minus d phi B by dt, negative of rate of change of magnetic flux. And EMF is basically voltage, potential difference. We know potential difference is negative of integral E dot dl. Okay, integral of electric field over a certain length gives you the potential difference. We know that. So, see, Faraday's law, what does it tell you? EMF induced in a loop. Fine. So we can say that that EMF is nothing but the potential difference in a loop. So closed integral E dot dl we can write. Minus minus cancel. It finally becomes like this. Closed integral E dot dl is equal to minus d phi b by dt. That is Faraday's law. Next, Ampere-Maxwell law. As we just discussed, closed integral b dot dl is equal to mu naught into IC plus ID, conventional current plus displacement current. That is Ampere-Maxwell law. These four equations put together are called Maxwell's equations. Okay. And using these four equations, you can explain everything about electromagnetism. Fine. In further studies, these will be very useful. For now, you just need to remember that these four equations are called Maxwell's equations. Nothing new. Only new thing that you learned today is the inclusion of this displacement current in Ampere's law. Okay. So Gauss law in electrostatics, magnetism, Faraday's law, Ampere-Maxwell's law. These four equations are together called Maxwell's equations. Fine. We'll stop it here for today. So today we discussed displacement current, basically Maxwell's discovery that a time varying electric flux produces a magnetic field. So time varying electric flux behaves like a current in the sense that it produces a magnetic field. So time varying electric flux is equivalent to some amount of current. That current is what we call displacement current. And how much current is it equivalent to? I is equal to epsilon naught d phi e by dt. And then we solve problems based on that. Okay. Fine, we'll continue on Tuesday. Tuesday's class, we will discuss properties of electromagnetic waves, how to write the equation of an electromagnetic wave, and based on wave equation, how to extract information based on frequency, wavelength, okay, energy stored in electromagnetic wave, all those things. Okay, thank you all. We'll continue on Tuesday.
Thank you, sir.